Hello. So far we have discussed mechanisms and we have gone through various mechanisms. So what are mechanisms? Mechanisms are arrangement of rigid bodies connected with movable joints to achieve desired motion, or every member or every component in that mechanism is describing a constrained motion. Now comes the time when we as well need to quantify this motion, right? So for example, if I take an example of a 4-bar mechanism, as we have seen in various inversions, let us say it is an inversion wherein it is a crank rocker mechanism. So when the crank is rotating, which is input, the output link is oscillating. The output link is oscillating. Now the question comes, okay, how much this output link is supposed to oscillate? That means I need to now, we have understood the motion, that at the forward stroke or the forward condition, the output link or the rocker is supposed to move, and at an extreme, when it reaches to an extreme, from there it will come back, then again it will reach to the second extreme, and then again it will return back. So that is how we have understood the motion, but now I have to quantify it, right? So now we are into this situation wherein we want to quantify this. Again, we can take the example of let us say a slider crank mechanism. So we know that the crank is going to rotate and the slider is supposed to translate between the two extreme points. Fine. Now I want to quantify this, or again as well comes the idea of how fast it should move. That means what we are talking about is displacement. First point. Second point, that means at what time, at what speed, or at what conditions it should do. That means the rate of displacement we are talking, so it is the velocity. And finally the rate of velocity, which is acceleration. So that is how now we are going to quantify this after understanding the motion. So I need to understand what is the displacement. Then I can figure out with the help of that what should be the, at the given conditions, what is the velocity. So that means how fast each member is moving in this given mechanism or given arrangement, as well as the most another important part is the acceleration, because we are saying that the mechanisms are rigid bodies. So certainly these rigid bodies will be having some mass. So in the dynamic condition, if these bodies are moving, so there will be definitely, like if you see the condition of the rocker is moving from one position to one extreme. That means at the extreme it is going to stop, and from there it will come back. So gradually again its velocity is going to increase. So that means it is going to again accelerate, reach to a max value, and then again it will move to the another extreme where it is going to stop. So that means from maximum velocity it will again move to the condition of zero velocity. That means it is retarding. So these conditions are changing. If these conditions are changing and this is a rigid body, then definitely the forces, the dynamic forces or the inertia forces of these bodies are also going to change, right? And that is why it becomes important for us, for a given mechanism, to plot the various configuration and conditions for velocity and acceleration. Now, so as if now we can understand, if I say talk about velocity, if there is a particle or a body, I'll consider this as a body or a particle, whatever right now we have to consider. So if we see the displacement, that means, let us say at one given point of time, this particle, say let us say this P is somewhere here, and after some time T, I see that the P has taken this position. So that means I can say that at certain time, this particle P has been displaced from its original position. So at another instant of time, I find it at a different position. So I can make out that it has, let us say, moved to the left. Fine, that means displacement is definitely have a direction, right? As well as how much it is displaced. That means it will be also having magnitude. So that means we can say that the displacement is a vector quantity as it is having magnitude as well as direction. Now that is why it becomes easier for us to analyze these mechanisms or to go for the quantitative analysis with the help of graphical method, because we can very well represent the displacement with the help of a vector, wherein the vector can be easily represented as I have shown you here. So maybe I can show it with the help of a straight line, and the arrowhead will give me or indicate the direction of the displacement. So in specific direction the displacement has taken place, and the length of this line is going to talk about or indicate the magnitude of this displacement. Now we are saying that this body has been, or this point or particle has been displaced from P to P dash at a given time t. So that means I can say that the ratio of this displacement with respect to time is the velocity. Fine. So when this is there, so we can very well again represent the velocity as well. Now if you see, simply this velocity is the ratio of displacement with respect to time. That means we can very well with the help of some other scale as well now represent the velocity, because it is just the ratio of this displacement with respect to time. So I can as well understand velocity, because this is also a vector, and definitely again the velocity is also having a direction. Now the direction of the velocity vector will be same as the direction of the displacement vector, and as well it will be having magnitude. So we can very well express or analyze quantitatively with the help of vector diagrams. Similarly then, rate of change of again the velocity will be the acceleration. So again acceleration is also having direction as well as magnitude. So this is also a vector quantity. So this becomes easier for us again to express all these quantities as vectors, and very easily we can go for the graphical representation. Right now, if we see, this is one of the best examples to understand. So let us say this is a slider crank mechanism. Now if you see this slider crank arrangement, now the slider, if you understand the motion of slider, the motion of the slider is pure linear. Whereas if you see the motion, or if you try to understand the motion of the crank, the motion of the crank is purely rotational. Right? And now if you see the coupler or the connecting rod, the motion of the connecting rod is, so if I take another instant, for example, say this is one configuration, and after some time it reaches somewhere here, so same length, now the motion will be something like this. So the condition of the connecting rod has changed from this to, let us say, it has moved here. That means this is have moved forward as well as it has turned. So it is having a combined motion. That is why this connecting rod here is also called as a floating link. So if if I'm saying that this rotational motion is converted into a pure linear motion, so gradually, like maybe we can connect it this way. So pure rotation has been partially converted into a rotational and linear motion with the help of the connecting rod, and then that partial has been again converted into a pure linear one, and this is due to the motion which we have given here. That means I can interrelate all these motions. In that case, this linear and rotational conditions we can as well interconnect and try to understand them. As we know, if I say, so as far as velocity of, say, if this is one body and it has taken a next position here, so it is a pure linear motion. So displacement vector, I don't have any problem, I can very well indicate it with the help of a straight line, right? As well as the velocity vector will also, so this is the displacement vector, let us say, and this is the velocity vector. They can be very easily understood because the velocity, direction of the velocity will be same as the direction of the displacement. So purely, so in the direction, so parallel to the direction of the motion, I can very easily draw these two vectors. But as well now we should understand, let us say there is this particle, some particle which is rotating about a point, or let us say a center O. Now in this condition, if you see, when this particle is continuously rotating about a point, that means the direction of the motion, of this particle about the center of rotation is continuously changing. Now in this case, if we see if we want to now relate, so now I can say that this is kind of, if the radius is not changing, then this particle is having pure rotary motion. Now this motion can be definitely about some curved path also, so I'll call that as a curvilinear motion. Here also continuously the direction of displacement is changing. Now, so that means how I can now relate the velocity vector then. So at the given instant, if you see, when a particle is rotating, a very easy example to understand is, if I tie a thread on a stone and rotate it, so the stone is having a continuous rotary motion, but maybe suddenly if I cut the thread, we find that the path traveled by the thread will be tangential to the path which it was following. So that means at this very instant, the path taken by that particle will be a straight path, and certainly this path will be a tangential path to the rotational path or the curve which it was following. So at this instant, I can relate the angular velocity with the linear velocity conditions, right? So for this, if we see, with the help of an arrangement, so let us say this is link 1 and we form a pair, so this is link number 2, fine, and let us say this link number 2 is having a pure angular motion, so the velocity is angular. Now I name this end, let us say this end is A. Now if this link 2 is having continuous or constant, let us say right now, rotary motion, pure rotary motion, we can very well say that every particle on this link 2 is having or is moving with the same angular velocity condition, right? So let us say it is omega, so it is rotating at, or every particle is rotating at the same angular velocity. Now let us try to understand and relate the condition. So after some infinitesimally small time interval, so this link 2 takes the position or moves, let us say here, So now I can say that means A has moved from here to say A dash, right? And this has happened at a very infinitesimally small time interval del t. So at this very small interval of time, this has moved to a very small value, infinitesimally small value of del theta. So here we can see that the motion or the displacement is a angular displacement, right? So when this is the condition, now we want to, if I want to understand the velocity conditions, what is the displacement of point A? I can say after an infinitesimally small value, the displacement is A dash, which is, or I will say that it is the arc A dash, right? So what should be the velocity? So velocity will be displacement which has taken place at infinitesimally small time interval. So that means it will be arc A dash by del t. But what is a arc A dash? It is a very small arc, and we know that for a very small arc, the arc length is almost equal to the chord length. So what is arc length? So I can say that this velocity is equal to, what is this arc length? Arc length is, say this is O. So OA, it is R into theta, right? Or R theta. So it will be OA into del theta at time del t. So we see that this velocity is equal to, this is the radius of rotation of point A about which it is rotating. So radius of point A, which is OA, into del theta by del t. So if we apply the limit condition, so we get this to be as V is equal to R del theta by del t. It is angular displacement by time. So this is the angular velocity. So V is equal to R omega, we can say here. And what is the direction of displacement? So it has moved, I have shown it to turn clockwise. So this vector or the displacement is from this A to A dash, that means which is towards left. So this vector will be the direction of this chord, right? And if this, for an infinitesimally small condition, you'll see that the angle between this radius OA, the vector is velocity vector is perpendicular to the radius, right? So I have earlier also said the path taken by when a point is rotating, it will be tangential. So if it is tangential, the tangent is always perpendicular to the radius. That means we get the velocity vector, the linear velocity vector, to be perpendicular to the radius of rotation of that particular point A. So that is how we can say, that means here now we can relate the angular velocity conditions with the instantaneous linear velocity condition. So this will be helping us to determine or get the velocity analysis or acceleration analysis. So we can very well draw the velocity polygon, then with the help of the velocity polygon we can draw the acceleration polygon as well. So we can determine the velocities of even the unknown points. So like right now, as I have taken this example, so this is link number 2. So now I'll represent it as a line. So this is link number 2, this is link number 1, and let us say this is one point which we have talked about, A. So when this link 2 is rotating at an angular velocity of omega, I can say that the velocity of A with respect to, if I name this joint as O, velocity of A with respect to O will be equal to radius. Radius is the radius OA, or simply here the radius is length OA into the omega of that link, so omega of OA, right? So that is how I can find out velocity of A with respect to O. Velocity of A, that is how it is indicated. Velocity of A with respect to O will be R omega, that means OA into, and what will be the direction of this vector? The direction of this vector will be perpendicular to the instantaneous link condition. So now if I want to draw the vector diagram for this, so I can first locate the pole of the velocity polygon. Let us say this is O. So I can understand from the given condition that omega is clockwise. So the velocity vector of A will be, so if it is clockwise, so it will be in this direction and it will be perpendicular to the link condition. So in the configuration diagram, I can draw this vector perpendicular to the link OA. So I can match my scale and I can draw one vector parallel to the link condition, given link condition in the configuration, right? And with the help of a suitable scale, I can decide that 1 centimeter, the length as how many meters per second or millimeters per second, and I can decide the magnitude. So if I know this value, then I can determine what is velocity of A with respect to O. I have understand the direction of this vector by reading the configuration diagram, and I can draw this velocity vector OA. So this is OA parallel to this condition, right? Now if I consider some other point, maybe somewhere here. Now as I have so told you, B is a point on the same link OA. Now if it is so, then both A and B, they are rotating at the same angular velocity, right? So the motion of the velocity of B is also in the same sense. So again, the velocity vector will be also in the same sense, which will be perpendicular to the link condition OA, right? So then what should be velocity of B with respect to O? Velocity of B with respect to O. So I am considering this point, so it will be the radius of rotation of that point. So that means it will be OB into omega of OA, because the link is same, right? So as the radius has changed, that means the magnitude of velocity of B with linear velocity magnitude of B with respect to O will be different than the instantaneous linear velocity of A with respect to O. But the direction will be same. So if it is smaller, then I will get this vector to be smaller than this. So again, from the pole B with respect to O, so with reference to O, if I draw, so maybe it will be a smaller vector. So this point is B. So I get the velocity of B with respect to O. So that is how we can represent. Fine. So right. So that is how then we can, for example, now we can plot the velocity vectors for any given configuration or any given mechanism, and we can try to understand. Now the best places to go for the velocity analysis are the joints. Now if you see the joints, joints are the locations which are sharing the links. So if it is, let us say O, A and B. Now if you see O is part of the frame. Now if you say A, joint A is on link OA as well as A is on the link OB. So if it is rotating in this fashion, so what we do in our analysis is we determine the velocities of the common points, that is the joints in the given configuration, and we try to plot the velocities with the help of velocity polygon. That's it for this session.